Hi class, this is Professor Smith. I'm going to be doing a movie on contingency tables, and so we'll start off by reading this problem. Fundamental attribution error, FAE, is the terminology psychologists use to refer to the tendency of a person to overemphasize dispositional factors and to underemphasize situational factors when attributing reasons to other people's behavior. We're interested in seeing if there's a difference in the inclination to commit FAE among groups that differ in the level of psychology training. So we're going to scroll down here to the contingency table. So let me change the resolution, or the zoom size I should say, so that you can see all the information. So we can see here that we have the level of psychology training of no psych training, psychological degree but not a psychologist, or a psychologist. And then we have here mostly situational, mixed, mostly dispositional. And so what we're going to do is answer the questions here. They've given here the observed values, the 9, for example. 9 people who did not have psych training attributed the reason to the situation, that a person behaved a certain way, as opposed to over here 36 of the people said no, they acted a certain way because that's their disposition to act that way, and then there were 16 that were mixed. And so these are observed values for each of the different levels of psychology training. So what we're going to do is fill in the blanks, and the fill in the blank says what would you expect to observe, or to expect to happen, or what we call sometimes the expected values. And what we're going to do is I'm going to go out to Word to capture how we would compute these 3 values that are blank. Now that I've opened up Word, I want to recall a couple of rules that we've already learned from earlier, and one of them is the multiplication rule. For independent events, say that the events are E and F that are independent, then the probability of E and F is given by the probability of E times the probability of F. And then another concept that we learned is in order to determine the expected frequency, it's just equal to N, which is the number in the sample size, times P, the probability of obtaining that particular event. For example, if we have 30% of the students are left-handed, we believe that's true for the population proportion of all students, then we would expect that if we had 100 students in our class, we would expect 30% of them to be left-handed, or 30 of them to be left-handed. And so we're going to use both of those concepts to come up with the expected frequency for our contingency table. So let's go back out to Alex so we can take a look at that contingency table. So we have here that we have mostly institutional. There were 30 of them out of 150. And we want to look at the the row total where it said 61 out of 150 had no psych training. So we want to say, well, what's the probability that that they're mostly institutional and no psych training? And so I'm going to write that information using Word. So we say mostly institutional, that value, when we go back out to Alex again, was 30, and the other one was 61. So we have 30 out of 150 times 61 out of 150. So that would be the probability that they're institutional and mostly, I think what it said was, oh my goodness, I've forgotten already. Yes, institutional and no psych training. So when we multiply those two together, that would give us the probability of being mostly institutional and no psych training. That's what we would have for the probability, or the proportion. And then when we say, well, what would you expect it to be? Well, it turns out then that would equal 150, that would be the n, and then we're going to multiply that times the probability, which is that 30 divided by 150 times 61 divided by 150. And so that gives us the n times p, n being 150, and then times the probability. Then you notice, oh my goodness, the 150s cancel. So it's equivalent to taking the 30 times the 61 and dividing that whole thing by 150. So another way to do this is to just take the column total times the row total over the grand total. So let's write that out. So it's going to be the row total, I said column total earlier, but it doesn't matter, times the column total, because multiplication is commutative, so whether you do the column total first or the row total first, it's okay. And then you're going to divide that product by the grand total. And that's our formula for finding each of the expected frequencies. So let's go out to Alex, use the calculator, and compute that for this problem. So we can see here we're going to take the 30, which is the column total, times the 61, which is the row total, and then divide it by 150. So I'll open up the Alex calculator, and then we'll take 30 times 61 divided by 150. And again, if I divide the last factor by 150 or the product by 150, the answer will be equivalent. And so we would expect there would be 12.2, even though we observed that there was 9. And then I'm going to hit the undo button, and I'm going to figure in this next grouping. So it's in the same column, so I'll still have the 30 for my column total, but the row is different, it's 54. So I'm just going to change the 61 to 54. And that will give me my new expected value. It's 10.08. Excuse me, 10.8. And then undo again. This one actually has a different column total and a row total, but we have the grand total stays the same. So the column total is 48. The row total, so 48 because we're in this column of mixed. And then the row total is 35 divided by the grand total of 150. And we have an expected a value or expected frequency of 11.2. And that's what you expect for the psychologist. And so then we'll hit next. This is very good practice again. So I think you got it. I just wanted to do a little movie just to show you how to do a contingency table. Alrighty, bye-bye. Oh, if you have any questions, feel free to call me at 916-813-9027 or send a text. Hi class, this is Professor Smith. I'll be doing a movie on chi-square chi-square test of independence. You're driving along, listening to the car radio and following the rules of the road, when all of a sudden a silver sedan comes out of nowhere and darts in front of you, causing you to slam on your brakes and spill your chicken nuggets all over the place. Why did that guy just cut me off? Most of us, drivers and observers alike, would tend to attribute his actions to dispositional factors. He's a terrible driver. He likes to scare people on the road. He was in a major accident as a child, and now he's trying to gain control of his fear by driving recklessly, etc. We tend to overlook the possible situational factors that may be contributing to his recklessness. He was dying. His dying son was in the car and he's rushing to the hospital, or he just spilled his own chicken nuggets and temporarily lost control of the car, or he's running from terrorists, etc. Psychologists call this tendency to attribute, often incorrectly, others' actions to dispositional factors rather than situational factors is called fundamental attribution error. We're interested in seeing if there's a difference in the inclination to commit the fundamental attribution error among groups that differ in the level of psychology training. So we choose three groups: adults to participate in a study, adults who don't have any psychology training, adults who have a psych degree, who are not practicing psychologists, and then those who are adults who are practicing psychologists. We show each participant a videotape on which a scenario similar to the one we described above was enacted. Then we ask the participants the questions about why the characters in the enactment behaved as they did. Suppose that our data are those summarized in the contingency table below, and I'll scan down to that in a minute. Each cell of the table contains three numbers. The first number is the observed cell frequency, F sub O. The second number is the expected cell frequency, F sub E. And under the assumption that the two variables levels of psychology training and type of attribution emphasized are not associated, and the third number is the value F sub O, which is the observed frequency, minus the expected frequency, that quantity squared, divided by the expected cell frequency. The numbers is labeled total, are totals for the observed frequency. Fill in the missing values of the table, round your expected frequency to at least 2 decimal places, and round this ratio, this expression, to 3. And then at the 0.05 level of significance, perform a test of hypothesis that the two variable level of psychology training and types of attribute emphasized are not associated. So it doesn't matter whether you have a degree or not a degree, are you going to make the attribution to dispositional or situational. Scrolling down to the table, we now have the values that they described earlier. And so what we're going to do is fill in the blanks. We're going to fill in the expected frequency using the same process we did for contingency tables, where we took the column total, multiplied it by the row total, and then divided it by the grand total. And so we're going to do this for the 1, 2, 3, 4 cells for which they have not given us that information. So opening up the Alex calculator, I'm going to compute each of those expected cell frequencies. And so for this one, the column total is 29. And then I'm going to multiply it by the row total, which is 58, and divide it by the grand total, which is 150. And whether I divide the last factor by 150 or the product by 150, you get the same value. So you get 11.21. And then I'll select undo and do the same thing for the mostly dispositional column. And so when I do that, I'll get the row total is still 58, but the column total now, instead of being 29, is 71. So I'll just change this to a 71. And I obtain the value 27.45. And then I'll go ahead and fill in the rest of those values and can come back to you. Now that I've filled in all the other remaining expected cell frequencies, 7.54, and then for the last one, 18.46, now I'm going to figure out the last value. And if I move my calculator out of the way, it'll show you exactly what that value is supposed to represent up above. So that last column of values is going to be this computation here. So let's do that for each of the cells. So since I have the value of 18.48 already entered for this particular one here, let me undo that. It looks pretty big. So 71 times 39, yeah, okay. So what I'm going to do then is I'm going to subtract. So I'm going to take 7 minus 18.46, and I'm going to square that quantity. Divided by 18.46. And this one I'm going to round to 3 decimal places, so 7.114. So I'm going to go ahead and compute the rest of those remaining values and then come back to you. Now working on the last value, 33 minus 27.45. So we have 33 minus 27.45 quantity squared divided by 27.45. And when we round that, we get 1.122. So that gives us the contingency table field. So now let's scroll down and finish out the rest of the problems that Alex asked us to do. So they ask us the type of test statistic, and it turns out when we have a test of independence or goodness of fit, that's going to be a chi-square distribution. And whenever you have a contingency table, in order to figure out the degrees of freedom, remember in the last one was goodness of fit, we were looking at several categories and seeing if proportions satisfied a certain criteria. It turns out with the contingency table, it's not just the number of categories minus 1. It turns out it's the number of rows, so that's the level of psych training, and then the types of attributes emphasized. So you can see here there's 3 columns and 3 rows, not including the totals. And so when you take a look at those, it turns out the degrees of freedom is 1 less than the number of columns and 1 less than the number of rows. So if you do 3 minus 1 times 3 minus 1, that's 2 times 2. So the degrees of freedom is 4. So let me capture how you would compute the degrees of freedom for a contingency table using Word. So it turns out the degrees of freedom for a test of independence is given by the number of rows minus 1 times the number of columns minus 1. So in our particular case, it was a 3 minus 1 because there were 3 rows and there were 3 columns. And so when we did that computation, it's 2 times 2, which is 4. So returning to Alex, we have in the degrees of freedom, which we had earlier, 4. So then to find the value of the test statistic, then we add up the values for each of those third computations. So we had the 0.436 and the 0.574. All those values we're going to add up. So I'll pull over the Alex calculator and you can see the values that I'm actually putting in. So we're going to add up this first value of 0.436 and then 0.574 and then 1.122, excuse me, yeah, 122. And then we're going to go here to this value, laptop is funny, and then we're going to go to this value of 1.03. And then this value of 0.403, 1.392, 1.7, 2.769, 7.114. And so what I'd like to do, just because this one's a little tedious and I don't want to do the problem several times, I just double check to make sure that I entered in all the values correctly. So 0.436, 0.574, 1.112, 1.03, 0.403, pardon me, 1.392, 1.7, 2.769, and I made a mistake, 2.769, and 7.114. And I would have caught it too, because 2769 would have been a huge chi-square value. All right, so then let's go ahead, and now we've found the test statistic of 16.54. Now they want us to find the p-value associated with this test statistic, and so I'm going to double click on that value. It's highlighted. Now I'm going to select the probability button for the chi-square distribution. It's always right-tailed, and the degrees of freedom we've computed already here of 4. So here, let me move the calculator in the screen so you can see what I put in. So I double clicked on 16.54. And then I selected the probability button for the chi-squared. The degrees of freedom is 4. And it's always going to be right-tailed, because we're looking at the differences between the observed and expected. If the observed is very far away from what you would expect, then we're suspicious that maybe there is some dependence. And so we get 0.002. All right, and so we ask ourselves the question with the p-value computation: is the p-value less than or equal to alpha? In our particular case, the alpha is given by 0.05, and 0.002 is definitely less than 0.05. That means, because of this difference here, I do believe that's the big one, that's pretty far away, and you square that. Whenever you find that's the case, then you know what we're saying, maybe there is a relationship there. So we're going to reject H naught, i.e. that they're independent, and say, I believe there's a dependence. So can we conclude that the variable level of psychology training and the attribution emphasized are associated? So we believe there is a relationship. We're not saying they're independent. So yes. Last time I took so long to do the computation with the movie that Alex timed out, so when I tried to hit the next button it didn't work. So let's see what happens. Oh. So, what did it say? The final value in row 3, column 1 is incorrect. Row 3, column 1. So row 3. So it's saying that value is wrong. So let's see. That, of course, will mess up your test statistic. All right, let's check it out. So it's 27.45. I bet that's the error I made. I bet I did 49, just like I just did. Minus 33. I know I put them in backwards, but it's all good, because when you subtract them and square it, it's still going to be the same value. Divided by 27.45. I should have had these switched, 33 minus 27.45, but when you square it, you're going to get the same value. All right. 1.122. Final value in row oh shush. Row 3. I'm in row 1. Remember I said I thought that was kind of big? Oh, it said the final value. All right, let's undo. Cuckoo Donna. So 7 minus 18.46. This is making my movie a lot longer. This is the one I did with you. No, I didn't. Yeah, it was. I don't know. 18.46. But I think you got the gist of the process. But it's nothing like seeing. Yay, you got it right. I get the same value. Oh well, I'll just hit explain because I'm not sure what I did wrong. Row 3. Oh, column 1. Do. Column 3, row 1. That's the one I had wrong. It's all good in the neighborhood. Yahoo! 7.54. What did I have? 3.94. I'm not sure what I did. If I knew how to edit this video, I would. Hey! Oh, that's the right answer. What did I answer? Wait a moment. Is Alex trying to jip me? 3.954. I'm confused. Oh well. I'm not sure what I did wrong because I don't know what my wrong answer was because it's not showing me what I put in. It's just showing the blanks. Oh, you know what? I can hit the back arrow. I bet it'll all be gone though. Oh, yeah, I totally jacked it up. Yep, I sure did. But anywho, you got the idea. Alright, I hope this video is helpful. My phone number is 916-813-9027. I could be vain and delete this whole thing and do one all over again. That's perfect. But I think it's kind of good to let you see that I'm human. Alrighty, thank you. Bye-bye.